Okay, so in this problem we have a human cannonball fired from a spring-loaded cannon at a circus. So if we picture this situation, it looks something like this. So the human cannonball starts here. So this is the guy. It, he's fired from this spring-loaded cannon. Let's call this y equals 0, and this point is y equals 7.5, such that the height is 7.5 meters. So this is a net of height 7.5 meters. If the human cannonball is fired and his speed at this point when he just crosses over the net, which is 7.5 meters long, is given to us to be 3.3 meters. We are looking for what is the energy dissipated to air resistance. Air resistance is like friction or air friction, you can call it. So this is non-conservative force. Therefore, we are actually looking for the work done by this non-conservative force. So this is a pretty. This question is more straightforward than before. We will need to use work energy theorem because actually our target is energy or work. Also, we couldn't have used Newton's second law because the spring force is weird. Spring force isn't a constant force, hence doesn't produce a constant acceleration, which makes our lives harder. We don't want to make our lives any complicated than it is already, right? So let's go over this other thing that is given to us. It is said that when the human cannonball is fired, the spring is maximally compressed at with a compression of 4.5 meters. So compression is the spring has an original length. It is being compressed by 4.5 meters before the guy is fired from it. All right. Okay. Then let's write out what our work energy theorem would be. We have Ki plus Ui plus non-conservative work equal to Kf plus Uf. Alright? Cool. What is Ki? At Ki, remember that we are going back again to 1 half mv squared because this is just for a massive object. This does like this, we can just consider this person to be of some mass m, which is given to us to be 68 kilograms, and the kinetic energy is given by this. Fine. At the initial point, this whole thing hasn't started yet. So initially the person was at rest. So this kinetic energy is also 0, right? What is the initial potential energy? Well, remind yourself that potential energy is always consisted of two things: the gravitational potential energy and the spring potential energy. Alright? Because there is both of these things present in this problem, we cannot set either of these to 0 at automatically. What we have to do is we have to investigate what these stand for. So let's remind ourselves that UG, the gravitational potential energy, is given by m times g times the height above the origin or ground level, and US, the spring potential energy, is given to us as 1 half k times the compression or extension squared. All right, compression or extension squared, that is the delta x, the length of the displacement from the original length of the spring. All right, so UG, that is the potential energy due to gravity, at y equals 0 is 0, right? So at this ground level there is no gravitational potential energy because there isn't any height above ground level. However, the potential energy due to the spring potential energy, is maximum because the spring is maximally compressed. It cannot like it wasn't compressed any below 4.5 meters over this whole trajectory of this person, right? So this is the maximum compression that launched this person. Alright, so this is actually non-zero and maximum. So the potential energy at the initial point will have zero gravitational, but some, all of spring potential. So 1/2 k times delta x squared. Delta x is the compression, which is 4.5 squared. Alright, and then we have the work non-conservative, which we are looking for. Let's use this. Work non-conservative, we don't know what that is. This is the work done by the air resistance we are looking to find. Kf is the final kinetic energy at final point when the guy just goes over this net. It is 1/2 m times 3.3 squared, right? And then what is the final potential energy? Now at the final point, the spring has already let the person go and the person reaches this final point. When the spring lets the person go, the spring goes back to its original length. As it goes back to its original length, there is no compression or extension. It just is equilibrium length. That means this displacement away from original length is zero. So if that is zero, then spring potential energy is zero. So at this point, the spring has returned to its original length. So this is zero. But after being launched, the person has gained some height above the ground, which is the height of the net. It just crosses over the net. So we can just consider the height to be the height of the net, which is 7.5 meters. Therefore, it has maximum potential energy. Mass times g times the height, which is 7.5. This is our equation we need to solve for W and C. We cannot divide off the m terms like we did before because not all of these terms on both sides of the equations have m. So we actually need a mass, and that is given to us. We also need this k. What is this k? Remember, this k is the spring constant of the spring in the question, and that is also given to us. So we have everything, and we want to solve for W and C. So let's keep W and C on one side and bring everything else on the other side. So 1/2 m is 68 times 3.3 squared plus mg. M is 68 times 9.8 times height, which is 7.5. Now subtract this term from both sides so that on this side we end up with minus 1/2. K is 780 delta x squared, so 4.5 squared. If you work all of this out, the work done by air resistance, or the energy dissipated to air resistance, comes out to be negative 2529 joule. So the work done by air resistance is negative because it is actually working against the human cannonball. Alright, it is taking energy away from the system.